in a separate video, I found what the general form of our spin matrix would be in an arbitrary direction defined by theta and phi in spherical coordinates. Now in this video, I'm going to go through at least the first part of trying to find the eigenvalues and eigenvectors of this matrix. Now the book, and what I typically call this, is Diagonalization, but it's worth noticing that within linear algebra, diagonalization usually means finding this inverting matrix as well. We're not doing that. We're just trying to find the eigenvalues and eigenvectors, and in this case we're going to be expressing it in the z basis. This itself is expressed in the z basis, and so we want our eigenvalues, well, eigenvalues aren't in the basis, but our eigenvectors are still in the z basis. We don't need that transformation matrix. So finding eigenvalues and eigenvectors is what we're doing. We might call it diagonalization, but it's not quite the same thing as what diagonalization usually is within a linear algebra textbook. So, first step is know what you're doing when you're finding the eigenvalues and eigenvectors. We need to find a vector, lambda, that when we apply this operator to it, we get back a scalar, lambda, and then a vector. Now, there's actually going to be two of them. We're going to have two different values of lambda. So maybe we could call this lambda 1 and lambda 2, lambda plus, lambda minus. There's going to be lots of possibilities. But the way I know that is because this is a 2 by 2 matrix. So we need to have two different eigenvectors to actually span the space. So now the next thing to do is to find our eigenvalues, right? So we're trying to find our eigenvalues here. And we're going to do that by using this characteristic equation. And so what that's going to look like is taking the determinant of this minus our identity matrix, so 1's on the diagonal, multiplied by lambda. And we expect that this is actually going to give us two different values of lambda. So this is going to look like cosine theta, and remember I use this bar to represent determinant. So that's coming from here. And one thing that's important is not forgetting that, like I just did. So h bar over 2 cosine theta, and now minus lambda times I. So again, we're on the diagonal, so there's a lambda. Now notice that this h bar over 2 can't really be pulled out front. That will mess up your determinant, and it's also not going to be distributed onto the lambda. So whenever you have a term like this out front, when you're going to do a determinant, it's really helpful to actually distribute it first. So then over here, I again have h bar over 2 sine theta, and now I'm using this contracted form for the phi. And in the other video, I went through kind of noticing that you had some sine phi and cosine phi terms that led to this. Now, because this is off the diagonal, this doesn't contribute because that identity matrix has a 0 here. Then I move down here, again, h bar over 2 sine theta e to the I phi. And then on this term, I have negative h bar over 2 cosine theta, and again, minus lambda. So now when I do the determinant, it's this down diagonal minus that up diagonal. And I'm going to run out of room on the board, but I at least want to show you the general process, and I might have to skip some steps. So let me actually move down to the very bottom of the screen. So I have h bar over 2 cosine theta minus lambda multiplied by negative h bar over 2 cosine theta minus lambda. And be careful with all of these minus signs, so I'm very generous with my parentheses. So this minus this upward term, which is h bar over 2 sine theta e to the I phi, and then h bar over 2 sine theta e to the negative I phi. Okay, so now this is really what we're going to be needing to do a lot with, because lambda is what we're solving for. So this is what's going to give us a quadratic equation, which will then give us two solutions. And it's worth remembering that this characteristic equation is equal to 0. So now, this is going to get a bit messy. Let's come over here and look at just what's happening in the second term. That's actually the simpler one. When you have e to the I phi times e to the negative I phi, that's equal to 1. So this is actually going to nicely simplify. So then, if I come up here, I'm going to try to distribute this out and see how I do. I'm going to have h bar over 2 squared cosine squared theta So that's coming from here, so that has a minus sign overall. And then I have these cross terms. Now notice, negative lambda times negative h bar over 2 plus negative lambda h bar over 2, the cross terms here cancel. And then I'm left with positive lambda squared. And then now I have this minus, and these terms equaled 1. So I'm not going to have to worry about this. I'm left with minus h bar over 2 squared sine squared theta. Does that look right? Okay. So now we're going to keep simplifying. Remember, your goal here is to solve, in fact, for lambda. So now you might think, okay, quadratic equation, need to get it into a simple form, or that certain form where you have like x squared with some coefficient x. The nice thing is this one's going to be pretty simple. Many times it's going to be a mess to solve for your eigenvalues. This one's going to simplify nicely. Notice that this has a negative h bar over 2 squared. This has a negative h bar over 2 squared. So negative h bar over 2 squared of cosine squared theta plus, because that minus sign's already brought out, which is why this is a plus, sine squared theta plus lambda squared. Hopefully you know this is equal to 1. Now what that means is I just pull this over to the other side and have now h bar over 2 squared equals lambda squared. Nice! Now, important thing. There needs to be 2 values of lambda. So if you say lambda equals h bar over 2, kind of, we have 2 values. We have lambda equals negative h bar over 2 and positive h bar over 2. Because obviously if you square negative h bar over 2, you still get h bar over 2 squared. So this is what I meant by we can actually call this lambda minus, and we can call this lambda plus. Now, this was a whole lot of math to tell you something you already knew. Because, think about it, when we were measuring spin up in z, what value did we get? The answer we measured was positive h bar over 2. When we measured spin down in z, what did we get? Negative h bar over 2. Same for x, same for y. The point is, any direction you measure, you will get up or you will get down. This is up in the n direction, this is down in the n direction. So all of this work is actually just telling us something we already know, but that's pretty useful. So it's helpful to go through this process and say, okay, now I have my eigenvalues. Now you have to go back and find the eigenvectors that in fact correspond to each one. This video is already way too long, and finding that eigenvector is going to be a little more mathematically intense than even this was.